Good afternoon and welcome at the fourth Tech Talk within the Tech for Impact campaign. This Tech Talk today will be entirely in English because of our distinguished guest, Anna Smith. So you have to forgive me for my accent. Anna is British, so well, that will be perfect. As frequent viewers of this program, or this Tech Talk, will know, I always tell a little bit about why we have a Tech for Impact campaign. So Anna, I will turn to you shortly, because the Tech for Impact is very, very important for the research within Delft. In Delft, as you know, fantastic things are happening, but to bring something from a brilliant idea into research, and from research into an invention, and an invention into practical use, these sound like small steps, but they're actually very, very difficult and cost a lot of money. And unfortunately, that money is not always there. And therefore, the University Fund of the TU Delft University will invest in this and try to accelerate brilliant research and try to be an incubator, actually, for technical research. And therefore, your donations can be an acceleration of innovative research in Delft. So it's very important, and I can't stress this enough. Please, in the end of this program, you will see a QR code. Use it and make the research of Anne make it more possible. But before we start with you, there's two small house rules. As you will have seen, we have muted all your mics, so unfortunately you can't change it. You're with too many, I've been told, so for people to start ask questions. But if you have a burning question, you can ask it in the chat, and we'll see it on the screen over here, and we'll ask the questions later. So, finally, Anna, welcome here in this Tech Talk. It's a great pleasure to introduce you as the fourth scientist in this campaign. You studied chemical engineering, and your interest in science brought you from France, where you were born, via England and Germany, now here to us here in Delft. And as a modern day version of Marie Curie, you investigate the intricate chemistry of fission products in oxides and molten salts. Well, only this sentence alone bezels me already. Your search for safe and sustainable forms of nuclear energy spiked absolutely the most interest among the Delft alumni. Because we've already received a lot of donations, and almost 1,000 people have registered for this talk. So there are a lot of people wanting to hear about your research.
Thank you.
Welcome, Anna. But first of all, how do you feel about your research being picked for the Tech for Impact campaign?
Well, thank you for the great introduction, and it's really an honor to be picked by the Tech for Impact campaign. It is really a chance to get some funding we would not get otherwise, of course, but it's also a great chance to tell alumni about our research here done in Delft, and to raise awareness about molten salt reactor technology. And I really hope that after today, the people listening will feel enthusiastic about the research we are doing and the molten salt reactors and how they can really help the energy transition.
Yes, because that's why you think that we need to give extra attention to your subject and raise awareness.
Yes, I think nowadays we have a lot of big challenges in front of us, the rising demands, the world population increasing, and we really need innovative solutions for the energy transition. And nuclear energy can be part of that solution, together with other renewable sources, wind, solar. And the molten salt reactor technology, as you will see in a minute, I think really has some big benefits that can really help in that transition.
And how can the donations to the Tech for Impact campaign help your research?
We usually get funding through European funding or NVO funding. And some of the research I will show today was started with NVO funding. We developed a setup, which I will show in a minute. And we need to perform more of these kind of experiments. And now we are at the stage where we build the first prototype, and we would like to build a version 2.0 of that setup to gain even more out of this type of experiments. And it's always difficult to get funding for a 2.0 setup. So, and I think the alumni donations are then really a great contribution to help fund this kind of work.
Well, I really hope, and I hope that all the people watching this will take note of this. We talked a little bit before, and when we talked about your research, I really saw there's a huge passion from you for this subject. Where did it come from?
Well, I started by studying chemistry. I went to the university in France, and then I went to England, and I did a research internship at the Joint Research Center in Karlsruhe, which is really a center of excellence for actinide research. And there I really became passionate about this nuclear materials chemistry. The nuclear chemistry is really fascinating, and like I said, I really want to contribute to the energy transition, and I think nuclear energy can play a key role in that. So this combination of very fascinating chemistry and the contribution I'd like to make to a better world in the end.
Yeah, well, we all, of course, want this, but I think indeed nuclear energy can bring a big difference. But why did you end up, when you went to all these countries, you ended up in Delft? How come?
Yes, so at the end of my PhD, there was a great opportunity to perform research at a university in the nuclear field. And I must say it's already difficult to find a position in academia, but there are also only a handful of places where you can do nuclear research. And Delft is actually the only university in the Netherlands where we can do experimental work with uranium and thorium. And I had the chance to start my research group there, which means that I could also explore research directions I would like. And that was really a great chance.
Yeah, and of course we have the Reactor Institute, the just opened Reactor Institute here.
Absolutely. And I should also mention that Delft has a really track record in the molten salt reactor field. So already for some years, Delft has been leading some research programs at a European level on molten salt reactor technology. So that was also very attractive because you have a lot of knowledge on reactor physics, thermal hydraulics, multiphysics, and so I had the chance to come and bring knowledge on nuclear chemistry.
Well, great, and I guess I'm not alone in really wanting to see what you're doing because, as I said before, you attracted a huge crowd, and I think most alumni that have looked at what you're doing or have this feeling that you can make a huge difference and when your research will succeed. So therefore, let's not wait any longer. The floor is yours.
All right.
And you have the thing.
All right. So with, as I mentioned just earlier, an increasing world population, increasing energy demands, and the need to reduce carbon dioxide emissions to limit the impact on climate change, we urgently need innovative solutions. Molten salts have inherently very interesting properties, and they can be part of solutions for innovative technologies that can help in the energy transition. They are used in thermal energy storage and concentrated solar power, for molten metal batteries. They can be used for pyrochemical reprocessing of spent fuel, and what we are discussing today, they are key for the molten salt reactor technology. The story of molten salt reactors starts in the United States around the 1940s. There were two experiments performed, first in 1954 with the aircraft reactor experiment, which ran at 2.5 megawatt thermal power, followed by the molten salt reactor experiment that ran successfully for 4 years at 7.4 megawatt thermal power with a fluoride salt. And from this experiment, there was a lot of knowledge gained. Unfortunately, this research was stopped shortly after for political reasons. There were more investments that went to liquid metal-cooled reactors. And it's not before the beginning of this century, with the impulse of the Generation 4 International Forum, that molten salt reactors got attention again. The Generation 4 International Forum selected 6 designs that should be safe, sustainable, economical, and proliferation resistant. And molten salt reactors were one of these designs. And we think that this one has really a high potential to bring clean, safe, sustainable nuclear energy. So I first want to show you how nuclear energy is generated today. Today, we are using mostly Generation 2 reactors, which are light water reactors, which means they are using water as a coolant, and this coolant is at around 300. The primary loop has to be pressurized 3 degrees Celsius, and to keep this high temperature, the primary loop has to be pressurized. The fuel itself is a solid fuel. It's a ceramic. It's uranium dioxide in the form of small pellets. It relies on the fission of uranium-234 core. And the fuel cycle relies on the fission of uranium-235. So when a neutron hits uranium-235, this one will split into 2 fission products, a few more neutrons, 2 to 3, and will release a lot of energy. And these neutrons can then go on for further fission reaction technology. Now, the molten salt reactor we would like to build is a really disruptive technology. It's not based on a solid fuel, it's based on a liquid fuel. And this has very interesting properties. With such reactor, because of the molten salt characteristics, you get some inherent passive safety features. You can operate the reactor at low operating pressures. The fuel cycle has a lot of flexibility, and molten salts, just because of their properties, show a good retention for fission products, which is something you, of course, like to have, because in accidental scenario, a concern is always if volatile fission products can come out of a reactor site. So I was mentioning the flexibility of the fuel cycle. In this type of reactor, we can use not only uranium-235, but we can also use plutonium-239, or even a fertile element like thorium. Thorium does not give fission in itself, but after capture of a neutron and a few steps, we get uranium-233 that is fissile, and this can give further fission reaction. Now, when we want to build this technology, we need to very carefully choose the molten salt that will be used as fuel. And this one needs to satisfy some very specific properties. It needs specific neutronic properties, some specific thermal and transport properties. Typically, you want a low viscosity of the salt for the ease of pumping. You want a high thermal conductivity to help the heat transfer. And what I'm working on are the requirements on chemical and thermal properties. We would like a high solubility of the actinide, so that means uranium, plutonium, thorium, such that we can get a lot of energy out of this reactor. These fuels should have a low melting point, so that we can have a lot of flexibility in the operating range while avoiding problems like corrosion. We want a high heat capacity, also for the thermal transfer. And we would like them to have low vapor pressures and high boiling point for safety perspectives. Finally, this salt should be compatible with the structural materials in contact with them. So why is nuclear fuel chemistry so important? Well, I think it's really key to the good performance of nuclear reactors. It will determine the behavior under normal operation, but also the consequences of an accident. And in that sense, studying nuclear fuel chemistry is really at the heart of the progress of Generation 4 technologies and of the molten salt reactor technology. So let's look first at what type of salt you can use in this kind of reactors. Historically, in the United States, for the aircraft reactor experiment and for the molten salt reactor experiment, some fluoride mixtures were used, and you see them here on the slide. They are made of a solvent and a fissile material. Maybe you could think, well, why are you not just using the fissile material? If we would use uranium tetrafluoride alone, this would have a very high melting point. That would not be possible for the reactor operation. So we need a solvent to reduce the melting point of a mixture. Very recently, and also since a few years, there are a lot of molten salt reactor concepts that are coming out in Europe. Since already a few years, a lot of European projects have been dedicated to the study of molten salt reactors, and they are mentioned here, Samophar, Samosafer, Endurance Mimosa. And more recently, a lot of startup companies propose also a design that they will want to bring to market rapidly. And in these, we have two families of salts that are used, either a fluoride mixture or a chloride mixture. And in any case, we always need a fissile element, we need a solvent, and maybe there is also a fertile element used in the mixture. This is the starting fuel, but once you put it in the reactor, things become more complex. First, you have a fission reaction. And that means that you will be generating during irradiation fission products. You can see these fission products on the periodic table of elements. They have colors, and already you see there are quite a lot of them. They can be soluble in the salt, or they can form metallic precipitates or be gas. And next to these fission products, you also have corrosion products. These accumulate after some time in the salt because this salt is highly corrosive. Typically, the structural materials you can use around the salt are nickel-based alloy, but in these, some elements like chromium are going to dissolve into the salt. So that will mean that these corrosion products will also affect the properties of the molten salt. So you can already see that we have the molten salt fuel with many elements. We add fission products, we add corrosion products. That makes a very complex chemistry. What we would like is to be able to predict performance of these types of reactors already at the design and engineering stage. We want to have models that can predict behavior in regions of temperature, composition, and so on, not available experimentally. And that's because you can never study the entire composition and temperature space experimentally. So you cannot have all the conditions in a laboratory as you will have it in a nuclear reactor. And finally, we would like to have models with very good predictive capabilities for multi-element systems, since once again you have the fuel, you have the fission products, and the corrosion products. Our approach in Delft is to start with experiments. Typically, we will measure the thermodynamics of the system, phase diagram, structure of the salt, and we will couple this with some molecular dynamic simulations, which will give us some more information on structure and other thermophysical properties, such as density, viscosity. Once we have this information, we can build thermodynamic models as well as density and viscosity models. We do that on the fuel system elements. We add fission products, we add corrosion products, and at some point we end up with a database on multi-component systems. This one allows us to do application calculations. So with our models, we can assess what happens at any condition in normal operation, but also under accidental conditions. Before I dive a bit more into the research we do in Delft, I have to give you a short crash course on phase diagrams. So I'm sure you did not expect that today, so here we are. We use this as a tool in our research. We are plotting the phases table in a system with temperature on the y-axis and fraction on the x-axis. Let's imagine you want to run a molten salt reactor with a mixture that has sodium chloride, basically table salt, although a very, very pure one, and plutonium trichloride. To be able to know at which temperature, which composition you are liquid, you need to do experimental measurements. And this was done in 1959. With that phase diagram information, these experimental points, the blue points, you know that if you are in the red region, you have two solids. That's not good for reactor operation. If you are in the orange region, you have a mixture of a liquid and a solid, also not good for the reactor operation. You need to be in the green region. I have put on this slide the ideal reactor operating window. We want a composition with a low melting point and one where you can operate without going to too high temperatures. Otherwise, you get into corrosion issues. So typically, that would be the operating window. But we cannot run a reactor with just a few experiments. We need to build models. So this is what we do. We build models using the experimental data. We also include the gas in that model, and we know with the model when the gas is stable. So we get information on the margin to boiling. And you can see that if we operate in this window, we have a very large margin to boiling to the temperature at which gas starts to form. So we can operate the reactor safely in that region. With that introduction, let's dive into molten salt chemistry done in Delft. We are always looking for promising fuel salts. And quite recently, we came across some experimental study done in 1976, long time ago, that was studying the system with sodium chloride, plutonium trichloride, and thorium chloride. We went on to model this system, and we found out that this one is really interesting for reactor operation. And why is that? If you look at the figure, you can see that we have two compositions that we call ternary eutectics that have very low melting points. So that's interesting for reactor operation. And then what do we have in this fuel? We have plutonium. Plutonium is produced in current light water reactors. There are stockpiles of it, also from military sources. So it would be ideal if we could burn this plutonium inside a molten salt reactor. This system also has thorium. Thorium is highly abundant on Earth. It's a fertile element, but becomes fissile within the reactor. And then again, it allows us to use a resource that is not used at this moment. And if we make further calculations, we see that this type of fuel has a large flexibility in the choice of fuel composition. We can stay at low operating temperatures while changing a lot the plutonium fraction or the thorium fraction, which means we can also choose the composition based on neutronic requirements or thermal hydraulics requirements. This fuel system, as I mentioned, is interesting. So now we study it as part of a European project called Mimosa. And if we want to get more insight, we need to make these salts. They are not commercially available. And that's a very challenging task because they are highly corrosive, they are radioactive, and they are air sensitive. So we need to work in glove boxes. Recently, we managed to make thorium chloride starting from thorium oxide, and that made us extremely happy, especially because we could get it with very high purity. We measured the sample with X-ray diffraction, and that's a technique that tells you about sample purity. It's a kind of fingerprint. And we saw we had a highly pure product, which is essential because in a reactor you want highly pure salts to make sure you know very well the properties and to avoid corrosion issues. Using a similar method, we went on to make uranium tetrachloride and after reduction, uranium trichloride. And we could even bring these samples to Grenoble at a synchrotron facility where we could do high resolution X-ray diffraction that confirmed really the very high quality purity of these salts. So we can use them to continue our research. In Delft, we cannot work with plutonium. So in that case, we need to find another way. We can use another element in the periodic table, cerium, that is a lanthanide element that shows similar properties to plutonium. So if we want to understand the effect of one fission product, I picked barium in that case, on the salt mixture, we can work with cerium instead. Let's imagine we have a mixture with sodium and plutonium trichloride, and we add barium. We want to know the consequences for the fuel chemistry. So we did some fundamental studies, and I will not go into the detail. You just see that we have a complicated phase diagram, much more complicated than the one we saw before. So we need to do structure studies, calorimetric studies, quenching experiments. But in the end, we get a detailed picture, and we get a model of that system. We can then build a model with 3 elements, the sodium, the barium, and the cerium. Cerium, you remember, is a surrogate for plutonium. And with that, we can make, again, application calculations. We can estimate what is the safe reactor operating window, which would be the green square on this figure. And what we see is that we can operate the reactor on this green window, but if the temperature would drop down, if we would come into region F, then we get into a region where we have a mixture of a liquid and a solid. This solid has the composition barium-3, cerium-2, Cl12. So with plutonium, it would be barium-3, plutonium-2, Cl12, which means we get plutonium precipitation. That's something we don't want during reactor operation. So it's important to know for the safety assessment. And this is only one fission product, but eventually we want to know what happens with many fission products. So we went on to carry work where we had a starting fuel that was sodium, magnesium, plutonium chloride, and we added a lot of fission products: barium, strontium, cesium, cerium, and neodymium. So we get in the end a picture of the chemistry of the irradiated fuel. With these computations, you can see what happens to temperature versus fraction of fission products. If we remain in the green region, we are liquid, we can safely operate the reactor. But if the temperature would drop down and we get in the red region, we get in a region where we have plutonium precipitation. Again, something we want to avoid. I discuss now precipitation, but there are other safety aspects you want to check during reactor operation. One of them is the change in melting temperature, and the other one is vapor pressure. We can build models, but it's also important to benchmark these models with some experimental studies. In that case, we started with a different fuel mixture, but the idea is the same. We started with a mixture with lithium, thorium, and uranium fluorides, and added now in the lab, experimentally, a lot of fission products to it to simulate irradiated fuel. And then we went on to measure the melting temperature of this mixture against the starting melting temperature. And we saw a lowering of the melting by about 20 degrees. We also studied the vapor pressure of this mixture and looked at retention of fission products. Typically, for the safety assessment, you want to know what happens with cesium or iodine. And this is what we did in this study. So this is all about thermodynamic information, but once we have this, we can also go one step further and model other important properties for the reactor: density and viscosity. Once we have a thermodynamic model, we can couple it to density modeling and also, in a third step, to viscosity modeling. And this is all done with a mathematical formalism called the quasi-chemical formalism in the quadruplet approximation. It's called like this because we used quadruplets, which you can see there on the slide, as the basic unit to describe the liquid. And that is very efficient, but it's still a mathematical description of a liquid. So in our group, we would like to go towards more advanced modeling. And why that? That's because there is a strong link between the structure of the salt and its macroscopic properties. If we take a salt like sodium chloride, that is a strongly ionic liquid. It is basically sodium cations and chlorine anions. But if we add uranium to it, we start to form complexes and a network of polyhedra. In a mixture with beryllium fluoride, you get a polymeric liquid where you form even dimers, trimers, and eventually polymers. This has a direct consequence on the microscopic properties. If we take the example of viscosity, we can see here in orange the viscosity of a lithium-beryllium fluoride mixture, and you see that this viscosity increases really by 4 orders of magnitude between lithium fluoride and pure beryllium fluoride. So that shows the direct link between structure and viscosity. In the case of the lithium-uranium fluoride mixture, we have an increase with 1 order of magnitude. Still something we need to consider. To study this local structure, we perform experiments at a synchrotron facility. We need to go to a synchrotron because we need a very intense and tunable X-ray beam. We use X-ray absorption spectroscopy, which is the measurement of the X-ray absorption coefficient of a sample. And because we want to measure the liquid, we need to do the experiments at high temperature and in situ. So we perform such experiment, we get a figure like this one, which is the absorption coefficient as a function of energy. And regions in this figure, a low energy region called XANES, and a high energy region called EXAF. It's the EXAF I'm going to discuss. That's the one we are interested in to know some more about local structure. To perform this kind of experiments, we had to build a setup. We had to design and build a specific measurement cell, which you can see on the picture. This cell is basically 2 boron nitride plates that encapsulate a sample. You can see a small pellet of that sample on the picture in between the plates. Boron nitride is one of the only materials we can use. It's transparent to the X-rays and does not react with the salt. Because we need to heat up the salt so it is liquid, we also designed and built a furnace. And to make sure nothing comes out, since these are radioactive salts, we also have a glove box around it, which we built also ourselves. So when we do these experiments, we go to the synchrotron facility with the cells, with the furnace, with the glove box, everything in the car, and then we get to the synchrotron. And we can start the experiments. You can see on the picture how everything is set up. The X-rays come from the bottom of the picture. They go through the measurement cell and come out. The X-ray intensity is then measured before the sample in the first ionization chamber and after the sample in the second ionization chamber. And with that, we can get the absorption coefficient. I'm going to concentrate on the EXAF region as I mentioned. After some mathematical treatment and some Fourier transform, we get the figures on the right, which we can fit. And when we do this fitting, we get information on the local structure. We can know how many fluorines there are around a thorium atom. In that case, we have, if you imagine you have a thorium in the center, you have fluorine ions around it at a distance of 2.3 angstrom, and on average you have 7 of these fluorines around the thorium. So that gives already some idea of the local structure. But if we want to have even more information, we need to combine the experiments with some molecular dynamics simulations. And we do that in collaboration with someone from Concordia University in Canada. With these simulations, we can simulate our EXAFS data. And if a match is good, and we can work to make sure the match is good, we have been validating the interaction potentials. And once we have this validation, we know we can get a detailed picture of the local structure at any temperature and any composition. And with that, we can know how the so-called chemical speciation looks like. So we can get a picture from the molecular dynamics on the formation of monomers, dimers, trimers, polymers as a function of temperature and as a function of composition. And all of this information we then use for the modeling. You remember, this is the quadruplet you see on the screen. The quadruplet is the widely used methodology to do this thermodynamic modeling, and I say it's very effective. But what we want is to use the structural information to have a more physical physically representation of the liquid. And to do that, we need the coupling of the experiments, of the molecular dynamics, and in the end, we can have this model of the liquid and the thermodynamics with some more physical basis. We believe that this will have better predictive capabilities using this coupled structural thermodynamic modeling. In the end, we want to gain a fundamental understanding of a local structure, so we can model not only thermodynamics, but also density, viscosity, and thermoconductivity. And this relation between structure and microscopic property, I think, is really key to get this fundamental understanding that is necessary to build predictive models when we will be dealing with multiple elements. You remember the fuel, the fission products, and the corrosion products. So with that, we really hope we can bring the technology readiness level of the molten salt reactor technology towards level 9, which will be the commercialization of this type of reactors. As a final note, I want to mention that this is not my own work, but really the work of a great team. In Delft, I'm really lucky because we have absolutely great technical support, and I'm working with a team of PhDs and postdocs that are highly motivated. And we also have bachelor students, master students that really come to the group, want to do research on molten salt reactors, and are also highly motivated. We also have great collaborations in Europe, with Canada, with people in the United States that all make this research possible. Thank you for your attention. And now I would like to hear your questions.
Thank you very much, Anna. Thank you very much. Please sit down. Take a sip of water. This was a very, for me, enlightening presentation. This is a subject where really I had to dig far into my
chemistry knowledge. Yes.
Yeah, to understand it. But I do understand the significance of this. We got an enormous amount of questions, and of course it's difficult to answer them all. We try to group them, and of course, and you mentioned it in your presentation as well. Safety is something very, very crucial.
Yes.
And there were a lot of questions about safety. And maybe it's not. Could you enlighten us a little bit more about
that? Yes.
And what can happen?
What can happen? That's a good, very good question. A molten salt, as I mentioned, has low vapor pressure. So that means that one of the things you are afraid of is that during a nuclear accident, some radioactive matter or some fission products will come out. And these fuel themselves have low vapor pressure. The fission products are retained well. What makes the reactor very safe is also the liquid nature of the fuel. One of the worst accidents is, of course, meltdown with a solid fuel. In our case, the fuel is already molten. So we cannot have the same kind of accidental scenarios. But the fuel in itself, because of its liquid nature, have really some inherent safety characteristics. So one of them is that if temperature rises, and that's what would lead in a solid reactor if things are uncontrolled to melt down. But in our case, it's already liquid. But if the temperature goes up, the fuel will expand. And because it's liquid and not solid, there's quite some space for expansion. And that means that the density will decrease. And then automatically, the uranium will become further apart from each other. So the fission reaction will slow down. So the fact that temperature goes up will automatically, inherently, bring the temperature back down again. So then that's one of the big characteristics. The other thing is that in this type of reactor, because the fuel is liquid, if there is an accident scenario, you can have some measure. You can drain the salt just by gravity. And so in all of these designs, there are some draining tanks that are also in subcritical geometry, and you can just let the fuel go down. So if you have an accident in the reactor core, the fuel can be dealt with outside of the core. And that's not something you can do with a solid type of reactor. So these are examples. Then one of the questions is what accidents can happen? And that's actually a very good question. And before we can bring these reactors to commercialization, we need the licensing authority to agree that all the safety scenarios have been checked and can be managed. And so molten salt startup companies are going to work together with, for example, the ANVS to find out how to define all these accidental scenarios. And it's not so easy for a molten salt reactor. So there's actually not a consensus yet on the type of accidents you can have because of the inherent safety features.
Exactly.
So you cannot have the same
because
kind
it's
of accident.
such a safe...
By the properties of the salt itself, right?
Yeah.
But still, people, of course, try to think of everything possible, and they classify accidents according to the severity. So you can have incident, you can have accidents, you can have limiting events, and how to deal with all of these.
Yeah.
But today, there's no easy answer to which type of accidents you can have. People are calculating what would happen in each scenario. Yeah. But one has to think really differently from a solid type of reactor.
Yeah, of course, and nuclear energy has this bad connotation that it's so dangerous, and this is safe.
And that's a design that is inherently safer.
Yeah.
Yes.
And in your experience in your lab, is that very dangerous?
We always work in glove boxes, so we make sure we work in safe conditions. These salts cannot be handled outside. I mentioned they are very air sensitive, so if you handle them outside, they will pick up water and decompose, so that's not something we can do. We always work in a closed environment.
And of course, again, that will stop the whole process.
Well, we are not in reactor conditions, so we don't have the same kind of potential accidents. The thing we want to avoid in the lab are contaminations. So you don't want to have the salt outside of the glove box or your encapsulation method. Yes.
But it's it's good to know, because you know how Marie Curie ended. So I'm very concerned about your.
No concern to have.
Okay. And another thing is of course talking about nuclear energy, nuclear waste, and I think this is also a very interesting field in what you're doing.
Yes, absolutely. Nowadays, some countries make the choice of not reprocessing fuel after it has been used in a nuclear reactor. That's what we call an open fuel cycle. And some other countries, France for instance, make the choice of a closed fuel cycle. Yeah. That means that after reactor operation, and I'm talking about the current generation of nuclear reactors, the fuel is processed so that you can separate the uranium and the plutonium from the fission products. And that's very important because they have very different decay lives. The fission products will be radioactive for about 300 years, while the uranium, plutonium, and what we call minor actinides, so these are things like americium, curium that are highly radioactive, will be radioactive for millions of years. So it's very attractive to separate them so we can deal with radioactive waste management of fission products for 300 years and do something else with the uranium and plutonium and minor actinides. And it's very attractive if we can reuse them to make new fuels. And that's one of the things we can do in a molten salt reactor. We can use the plutonium and put it back into the reactor to burn it. So then this waste becomes a resource because you use it to run your reactor, which also means you don't have to use new uranium sources. You can use the plutonium you have generated already anyway.
Yeah, and the rest of the waste is actually manageable well in 300 years.
It's much easier to manage waste for 300 years than it is for millions of years. Yes, exactly.
we also got a lot of questions from I think the more learned part of our audience that ask questions about the corrosion and structural materials that are most suited to withstand the harsh environment of the reactor. Example, Kevin Gill and Michiel Mensink and Hans Montebaum asked this. I hope that they're in the among the audience that they now hear your answer.
Yes. I mentioned these sources are very corrosive, so one of the challenges for the technology is to find some structural material that will withstand the corrosion of the salt. And there are different choices. Historically in the US, they used some nickel-based alloy, an alloy called Astelloy N, that showed to be really very resistant to the fluoride salts. And nowadays, molten salt startup companies have to make a choice. Are they going to use Astelloy N or are they going to use another material? One tricky thing is that if you want to use a material in a nuclear reactor, you need to go through a certification process. So typically, stainless steel 316 or 304 have been certified for nuclear applications. So maybe Astelloy N is attractive because we know it is quite good at resisting the corrosion of the salts, but it would need to go through this certification process, which will take 10 years, 15 years.
Oh.
So some startup company make the choice to use stainless steel that has been certified instead. We are doing some experiments within the Mimosa project. We have a PhD on that, where we are looking at the corrosion of some steels, some nickel-based alloys, and we will also look at ceramics to get a fundamental understanding. And we can probably find a very good material. But if we want to build a reactor fast, I can understand that some startup companies will say, I take the nuclear certified one, and what I do is that I will only use this material for 3 or 5 years. And I know it can withstand 3 or 5 years, and after that, it can be replaced.
It's frustrating when the licensing process is slower than the research.
Yes.
And then we really got to worry about what we're doing.
But there are many things, of course, that need to be taken into account.
And Helen Uitslag and Adriaan Klooster had the same question that I had actually when I was reading about your research. What's the biggest challenge actually now for you?
There are many challenges for commercialization of molten salt reactors. If I think about the chemistry itself, I think one of the big challenge will be to upscale the production of the salts with very high purity to the volumes you need for a molten salt reactor. We see how it is difficult in our lab, and we are just working at a gram scale, but we need much larger volumes for a molten salt reactor. So I think that will be one of the big challenges. Also, what we are working on, being able to predict in a very reliable way what will happen, what will be the behavior when we have all of these elements. You have half of a periodic table in your salt. That's very challenging.
Yeah.
But if we think
it becomes a big soup.
It becomes a big soup, exactly. And if we think more largely, some other challenges for commercialization will be this licensing process, because we have to think of completely different scenarios for accidents compared to a solid reactor.
Yeah, and then every country is doing its own licensing.
Exactly, so every country will be also a bit different. And the other thing is that this technology is not just one reactor type. There's a wide variety of reactors. They all have different sizes. There's even a taxonomy that classifies molten salt reactors in 6 families. So you can imagine how diverse it is. So each licensing has to be adapted to also one designer. Yeah,
but, and it's actually it's close to another question. For example, Erik van de Grient asked, which resources can be used to run a reactor? What can you put in your soup?
So in the soup we can put uranium. We can put uranium-235, but we can also use thorium. So that's quite interesting because thorium is very abundant on Earth. It's about 3 times more abundant than uranium. So we can use this fertile element, and then we have a fuel that within the reactor becomes a fissile element, uranium-233. So it is self-sustaining, making fuel within the reactor. And we can also burn plutonium.
Yes.
So plutonium coming from the stockpiles of current light water reactors.
Yes. That would be actually then you would clean up nuclear waste.
So that's what I really feel enthusiastic about, is that we have a technology that can clean up this nuclear waste. So you also bring a solution to another problem of nuclear energy.
Yeah. And of course, we've got a lot of questions, economical questions about the economical viability of all this, and of course also political questions. And of course, and I can understand for you as a scientist, you want to stay away from the lobbying and you know, and we all can see your enthusiasm for this. But still, what do you think about the viability of this? Do you think this can actually work, and in what kind of time frame?
Yes, I think the concepts that are coming out, that are designed nowadays, we have more startup companies in France, in Denmark, and also in the Netherlands. There is a startup company called Horizon that is half Dutch, half French, that is also designing a reactor, are designing mostly smaller reactors compared to light water reactors. So you have typically reactors between 40 megawatt electric to 300 megawatt electric. And the fact that these different designs are generally smaller, but also can adapt their power, brings a lot of benefits. You can use it for a lot of different applications, and also you can use it at remote locations or close to a town with some population to provide electricity or heat. So I think this flexibility of a molten salt reactor means you can use it at a lot of different locations, and in that sense I think there is a real benefit also for the Netherlands.
As a small country.
As a small country, and also I mean in Europe, if research is done and here it can benefit for the.
But this technology is also you can also use for what's now really hip. I hear this a lot about the mini reactors that Google wants to order. Is this technology could work for that as well?
So these some of these reactors could be classified as small modular reactors. So the ones that could be used not only for electricity but also for industrial heat, for data centers, for mining activities, for steel industry, where there is a need. There is a need. Yes.
We also got some questions from the audience, and one of them was, with all the startups around the world, how do you make sure your research hasn't already been done before or is being done by another group or team? I mean, how would you know?
Yes, how would I know? Well, it is clear that if some research is done in the United States and kept confidential, I will not know about it. But the nuclear fuel chemistry is not really something you can patent, so the intellectual property is not so sensitive. So I think we know a lot of things going on, so of course through papers, but we also have some communication with other labs in Europe, within our European projects, and in labs, for example, in the United States, there is some discussion going on. So we know also what's being done. I must also stress that I think there is a difference between the research we do at university, which is fundamental study. We want to really understand the basics of the system. And then at a startup company, if research is being done, they want to bring the technology to market. So they will maybe test the salt composition they have selected to put in their reactor, while we will be studying a wider composition space. Just to give an example. But we also have, so through European projects, I can mention one, Endurance, that just started in October. This is a European project where we want to reach out to national labs in the US, also labs in Canada, and at other places in Europe, to start what we call a round robin. We want to measure properties of a salt, and we need to do it. We want to do it with other labs because these are actually difficult measurements. So we want to share experiences and we want to come in the end. We want to define best practices, and for that we are going to reach out to labs in the US. So there's also some collaboration.
And if people are concerned that there's another place in the world where they're also doing this and they might beat you, I would advise them, please donate to your research, and you can go even quicker.
And then we can go even quicker.
And then we can be assured then that you're in the front runner in this in this research. And another question that comes from the audience and was also it's something that we all want to know. What's the final goal of your research?
So my ideal outcome would be that we build these models that are multi-scale. So going from the atomic level, where we have a description of the local structure, to the macroscopic scale, where we can measure in a coupled way the chemistry and also properties like density and heat capacity, viscosity, thermoconductivity. And we want to be predictive in the end. And that is really essential for the safety of a reactor.
Yeah.
And that I think is something really essential if we want to build such reactors, to have this very comprehensive understanding and modeling capability.
Yeah. So what you're making is sort of the cooking book, for the reactor making the soup.
To open a page and then find out what happens.
And start making the soup.
And start making the soup, yes.
And I thank you so much. It was extremely interesting, and really your research has been selected for this year Tech for Impact campaign, and not for nothing. I mean, this will make a big difference. Your contribution can't be overstated. I think it's fantastic, and say please, if you're viewing this, realize that really, we have to keep you in the front of this very important research, for not only for the Netherlands, but not only for Europe, but for the world, for safer nuclear energy. So if you want to donate, I hope that you see a QR code in your screen. You can use this, but I think have been the notes or in the chat, ways of donating have been sent. And if you can't find this and are still wondering how to donate, please drop me a note. You can find me on the internet. My name is Jasper Pieterik. I'm the director of the University Fund. And I'll help you, and because we really want to help your research, your valuable research, to go on. I thank all the audience for viewing. I hope my English wasn't too bad, and you were able to follow it. This is for this year, unfortunately the last Tech Talk we had, but I'm sure we'll do it again next year. And please keep us informed about your progress.
I will. And
thank you again for joining us here.
Thank you so much for inviting me.
Absolutely. Yes. Well, thank you. And I hope to see everybody in 2025. Thank you.